Welcome to today's chemistry lecture. In today's lecture, we are going to study the furthermore three factors that affect the rate of reaction. So, without wasting time, let's start our today's lecture. The first factor is reactants present in a gas phase. When reactants are gases, their concentration dynamics are directly managed by alternating presence pressure condition. For example, the pressure concentration leaks. How? For gases, increasing the pressure forces the gas molecules closer together, effectively increasing their concentration per unit volume. For the second, proportional rate increase. Because the particles are moved crowded, the Clausian frequency rises. For example, hydrogen plus chlorine. The rate of reaction between hydrogen gas and chlorine gas can be precisely doubled if the pressure of the chlorine gas is doubled, provided the hydrogen gas is present in excess amount. The other factor is effect of surface area of solids. For heterogeneous reactions involving a solid reactant, the chemical reaction can only take place on the exposed outer surface of the solid. For example, surface area exposure. The rate of reaction depends heavily on the total surface area available for physical contact between the reactants. Fine divided solid versus large pieces. Smaller particles means powder or fine pieces expose a vastly larger total surface area than a single large lump of the same mass. This exponential increase in exposed surface allows more reactant particles to come into contact simultaneously, driving a high rate. Let's understand this concept with example. First example is aluminium and hydroxide. Sodium hydroxide. A smooth sheet of aluminium foil reacts slowly with warm sodium hydroxide. In a finely divided state means powder or fine fillings. Aluminium reacts rapidly even with the cold aqueous solution of hydroxides, violently evolving hydrogen gas. Second example is combustion of wood. A single large piece of wood logs burns slowly, where the same mass split into small twigs or woods shaving burns rapidly. Means if we use a single large piece, it will slow down the rate of reaction, whereas we divide that mass into fine or small pieces, the reaction will rapid. Let's see the other fact, which is effect of temperature. It is a universal everyday observation that the rate of chemical reactions increase when the temperature of the system raised. Real world examples, for example, cooking. Food cooks much faster at high temperatures than at a lower temperature. Rusting means oxidation of iron. This process is essentially slow and gradual at room temperature, but proceeds very quickly at high temperature. The exponential trend as shown in figure 17.6. The rate of reaction does not just increase linearly with temperature, it curves sharply upward. In many chemical systems, the overall rate of reaction doubles for every 10 degrees Celsius increase in temperature, as we studied this concept in the previous lectures. Here comes the Clausian theory mechanism for temperature. First, raising the temperature directly increases the kinetic energy of reacting particles. Second, this increase in energy increases the velocity, speed of the movements. Third, faster movements significantly increase the frequency of collisions per second. Fourth and last, more importantly, it dramatically increases the number of particles that possesses enough energy to clear the activated energy barrier, significantly enhancing the frequency of successful effective collisions. Here is some interesting information which state that industrial benefit. A thorough industrial understanding of reaction kinetics allows chemical engineers to optimize the reaction condition and factors. This helps to maximize the product yield while minimizing the chemical waste and the energy expenditures.